Hello, everyone. My name is Shivshankar Kumar, and today I am going to present my concept for the Modified Invisibility Cloak. First, I want to make one thing clear. This concept is not like traditional science fiction. We are not bending light here. My device is a Perceptual Illusion System. In simple terms, it operates like a digital window or a perception platform. It creates a visual trick, causing your brain to perceive that the object has become transparent. This entire core mechanism works in a continuous three-step cycle: sensing, processing, and displaying. Sensing, step 1, first, precision observer tracking. Algorithms track your exact 3D position and viewing angle. Processing, step 2, at the same time, cameras on the cloak's opposite side perform dynamic background acquisition, and the system warps that background according to your perspective. Displaying, step 3, finally, that warped image is displayed on high-fidelity OLED panels. First, we have a hollow cubical frame. As you can see, this is the main skeleton of our cloak. Its dimensions are 250 cm by 250 cm by 250 cm. Now, inside this frame, we install the necessary hardware. This includes a processing unit, like a Raspberry Pi 5, a power and cooling system, observer tracking cameras, background cameras, and ambient light sensors. The next step is to assemble the skin. We attach OLED panels to 5 faces of this frame, excluding the bottom. These panels are what cover the device. And this is the final result. On the left, you can see the internal structure, and on the right is our fully assembled cloak in its off state. These black OLED panels are what will create the illusion when activated. So, how does this cloak work? It's based on a simple 3-step process. The first step is data acquisition. 2 things happen here. First, observer tracking cameras track the observer's face, angle, and 3D position. Second, opposite side cameras capture the live environment feed from behind the cloak. The second step is scene calculation. Here, the data we've collected is processed. If the observer is face on, the system performs a direct calculation. And if the observer is edge on, our special edge illusion management algorithm is used, which performs seamless stitching. The final step is dynamic, seamless projection. The calculated scene, whether it's direct or a stitched image, is projected by the system onto the cloak's OLED panels in real time. And what is the result of these 3 steps? An illusion of transparency, invisibility. The observer feels as if they are looking right through the device. So let's move into our testing environment. This is our high-tech demonstration lab. On the walls, you can see our core principles: 3D tracking, perspective warping, OLED display. Now, we place our main device, the hollow cubical cloak, in the center of this lab. Notice, the device is currently off. That's why you see it as a normal black cube. Our goal is to hide an object inside this cloak. As mentioned in our text, we are covering a 7-foot dummy man inside it. Now, look at this image carefully. The cloak is not transparent. This image is only to illustrate that a dummy man is placed inside this black box. Our challenge is to make this dummy and this cloak disappear together. So now let's begin. Scenario 1, face-on observation. In this scenario, we'll see what happens when an observer looks directly at one face of the cloak. We've placed the cloak in the lab, and this blue circle is our observer's position. Now we introduce our observer. As stated in our text, our observer is a 4-foot child. This child has now moved to that specific position and is looking at the left face of the cloak. This image perfectly summarizes our scenario 1 setup. Inside the cloak, there is a 7-foot man inside cloak. Outside, we have the 4-foot child tracked observer. And our goal is crystal clear: vanish for the 4-foot observer. We want this device, along with the 7-foot dummy, to completely vanish or become invisible for the 4-foot child's perspective. So, as soon as the child took their position, the cloak activated and step 1, data acquisition began. As you can see in this image, it has 2 main parts. Observer tracking. The system has started tracking the child's face, angle, and 3D position. Background capture. At the same time, cameras on the opposite side, behind, have started capturing the live video feed of the environment behind it. As soon as the data was acquired, step 2, scene calculation began immediately. What is the system doing now? It's using the data from observer tracking, meaning the child's 4-foot height and 3D position. Using this data, the system is calculating the exact scene that should be behind the cloak, specifically from that 4-foot child's perspective. And this is our final step, step 3, dynamic projection. The scene that the system calculated in step 2 is now being transferred or projected by the system in real time onto the cloak's left face OLED panel. The result: it looks as if they are looking directly through the cloak and the 7-foot dummy inside it. So in scenario 1, we saw how the cloak created a perceptual illusion on the left face. But what happens if the observer changes their position? Look at this image. Our observer, the 4-foot child, has now moved in front of the cloak's right face. As soon as the child moved, the cloak's observer tracking cameras instantly tracked their new 3D position. And now, that same 3-step process, acquisition, calculation, projection, has activated independently for the right face. This proves that each face of the cloak works independently. But now we will test the system for a new challenge. What happens if 2 observers look at 2 different faces of the cloak at the same time? As you can see in this image, we have one child in a yellow shirt looking at the left face, and a second child in a red shirt looking at the right face. And this is the result when we activate the cloak. The cloak has successfully become invisible for both children at the same time. This is possible because, as stated in the text, the same process occurs on other faces of the cloak independently. The system is running 2 separate 3-step processes at the same time. In scenario 1, we saw a successful face-on observation test. But now we come to our most critical test, scenario 2, edge-on observation. Look at this image carefully. Our observer, the child, is no longer in front of a single face. They are placed in front of one edge, meaning at the join of 2 faces. This is our new setup. The goal of this setup is to explain how the cloak achieves a seamless perceptual illusion of invisibility when the observer views any one edge. This is much more difficult than scenario 1. For this, our normal 3-step process is not enough. The system will need additional algorithms. In scenario 2, our first step is also data acquisition. As soon as the child took position in front of the edge, the system activated observer tracking cameras near that edge are continuously tracking the child's face, angle, and 3D position. Background capture: at the same time, cameras on the opposite side are capturing the live video feed. Now we come to the most important step of scenario 2, step 2, edge scene calculation. This time, the system has activated additional algorithms. We call these algorithms the Edge Illusion Management Algorithm. This is the dedicated intelligence designed only to manage boundaries or edges. What does this algorithm do? It detects the edge view. It selects and routes 2 separate background camera feeds. It stitches those 2 distinct feeds to create a single, coherent background image. It calculates a compound viewing vector, so the perspective transitions smoothly across both panels. And finally, it applies ingredient feed blending to the physical panel seam to achieve zero visual discontinuity. And this is the final step, step 3, seamless projection. The system is now taking the final output of the Edge Illusion Management Algorithm, that seamless, stitched background image, and applying the observer-specific perspective warp to it. This combined image is now dynamically warped and projected across both adjacent physical OLED panels. The result: absolutely no visual discontinuity. The illusion is now perfect, even on the edge. Until now, we have tested our cloak in a stationary position. But now we are doing a new and advanced test, the moving scenario. As you can see in this image, we have placed the cloak with the dummy inside on a moving cart. But now we are taking this challenge to the extreme level. What happens if the cloak on the cart is moving, and our observer, the child, is also in motion? And this is the result of the extreme mobility test. You can see, the child, moving observer, is walking around the moving cloak. They are moving from the front to the side, and then to the other side, and the cloak is successfully maintaining the invisibility illusion from every angle. This is working for face-on and edge-on conditions during real-time motion. This is possible because it falls within a particular case. First, we have a single observer. Second, the relative speed of both cloak and observer is very low, like 20 km per hour. In these conditions, our processing unit is able to handle that extreme computational load. So we've seen that this cloak works. But this isn't just a single device, it's an entire perception platform. Using its core principles, like observer-specific warp logic and ambient-aware blending, we can create many other visionary products. The first application is the AI window. This is a digital window that can give the sensation of a real window, even on a solid wall. It uses the cloak's core components: outside cameras, observer tracking, inside the room, and OLED panels. As you move, the view outside the window will dynamically warp to your exact eye position. Next is the AI door. This takes the AI window concept one level further. Before this door opens, it displays a live feed of its background, like the hallway, warped to your perspective. It uses edge illusion logic to appear completely seamless with the wall. We can also add gesture control. This is a very special application: AI office walls. Imagine a central boss's cabin, with walls covered in OLEDs. The system will only track the boss as the observer. Then, it will stitch and warp live feeds from the employee zones onto the walls. This gives the boss the feel of an open space, transparent office, while maintaining physical privacy for the other employees. It's a one-way illusion. Next is the invisible glass bridge. This is a public installation that will give the effect of walking on air. It would have transparent OLED panels underfoot. Cameras placed below, like the view of a canyon or city, will capture the view. Overhead sensors will track your angle and project the perspective-correct view onto the floor. It's structurally safe, but provides an unbelievable thrill. This is the invisible suit. It's a wearable system designed to make the wearer invisible, but only to a single, targeted observer. The entire suit would be covered in micro-OLEDs and cameras. It captures the surroundings and displays them specifically in the viewing direction of that target observer. This isn't mass invisibility, but rather a highly targeted, observer-specific illusion. Thank you all for your time and attention. This was my complete concept for the hollow, cubical invisibility cloak, and its applications as a perception platform. Now, I have one request for all of you, the audience. If you like this concept, and most importantly, if it sounded logical to you, then please go to the comments section and honestly rate this concept out of 10. And if you have any questions related to this, my Instagram ID is in the description. You can ask me by sending a direct message there. And now, I want to make a special request to R&D organizations, technology companies, and universities. I know that building this will not be easy, perhaps not as easy as it looks in my presentation. We will certainly have to face some challenges to make this a reality. But if you feel that this invisibility cloak and its commercial applications can be built using this concept, and you want to collaborate with me to make this a reality, then please email me. My email ID is also given in the description. I have spent many days researching this concept, and I have prepared a detailed blueprint for it in the form of a PDF. I am also currently researching another science fiction device, and that is also nearing completion. My aim is to try and build science fiction devices using current technology, and you have just seen one example of that. Thank you.